Thank you so much for inviting me to have a talk today. And yeah, it's my honor to be a member of MOBI. And thank you a lot for letting me join the MOBI organization. And today I'm going to talk about the high performance blockchain accelerator. Icon is BCA, architecture that's supporting the Society 5.0. So uh, before my talk, so let me have a minute to introduce about my university, Nara Institute of Science and Technology. Okay, so as you see here in this map, this is the map of Japan, a part of Japan, and my university located in this area. So if I enlarge it, so my university near to the big cities like Kyoto, Osaka, Kobe, or a little far you see Nagoya cities, a big city in here. So my university is one of the two public schools that only educate the graduate students. I mean master and PhD course only. And we focus on three main subjects: information science, material science, and bioscience. And you see here, this is the map of my university. We have some building for information science, bioscience, material science, some building for administration, and the dormitory of student and staff. And we have about 200 professors and 200 officers. For students, we have only more than 1,000 graduate students who is researching in master and PhD course. And there are about 30% of students are foreigner students, which come from more than 40 nations, and most of them come from the Asia countries. Yeah. So when you have chance, so please come tonight to have some invited speech to our students. Yeah. Welcome you tonight someday. Yes, and about my talk, so I divide it into three parts. The first part, I give a background about the blockchain technology that I think some of the knowledge may be important for you to understand my content in the part two. And in the part one, so some knowledge is maybe too basic. It's suitable for the student or for someone that's beginning to study about blockchain. Therefore, so if you're a MOBI member and you're very expert about this field, so maybe I think this part is, you may feel bored about that. I'm sorry. And about the part two, I explain about our proposed work about high performance BCA architecture. Because of the limitation of the time, so I basically introduce about the basic ideas and then the result that we get. And the part three, very short. I just briefly explain about our prototype blockchain system that we are doing now. Okay, so let's go to the first part. What and why blockchain? Very short introduction. As you know that blockchain is a decentralized network in which the data of on the user are stored in a blockchain ledger, stored in the block, and the block connected together and it's formed a blockchain ledger. The characteristic of the blockchain network is that it's decentralized. The first is decentralized, in which the blockchain ledger here is stored decentralized in a lot of computer distributed around the world. Yeah, this feature is very important. That make the data can be shared among the user, among the organization, among the service, which is very important. And the second characteristic, very important characteristics of the blockchain network is that the ledger here is immutable. It means that once the data is written into the ledger, it cannot be removed. It cannot be changed or cannot be deleted. Yeah. And then it's transparent. It means the data here, the shared data is available for the people that is expected to see that data. Yeah, because of this most important characteristic, the blockchain is said to be very important technology to develop the super smart society 5.0. Now, currently, it's successful for governing the cryptocurrency system, but it's also very important to build a smart system for self-driving car ecosystem or smart healthcare, push trust, or supply chains. Yes, a lot of application for the blockchain. Okay, before we go more detail about that, so we talk about the VIP, the very important factor of the blockchain that the blockchain network want to protect. So that is the asset owner relationship. As I think that in this world, everything has the owner relationship. For example, some things belong to someone. Yeah, everything in this world is have the such kind of relationship. So to describe about the owner relationship, we go in three steps: identification, authentication, and authorization. So how it show in our physical life. For example, the identification is mean that it claimed to be a certain person or certain things, who you are, something like that. And authentication is mean that the other people verify that you are really who you claim to be. And the authorization is mean that granting the access after a successful authentication. Let's say you buy a ticket, the air ticket, and you want to go to the airplane. Then the identification is mean that you go to the airport and you say that, oh, I'm ABC. I already buy the ticket, so now let me get in the plane, something like that. And the authentication here is mean that the officer, the airplane officer, they will check your ID card, your passport, to see that whether you are really who you claim to be or not. And if you pass the authentication, you get the authorization. You have the permission to get on the plane. Yeah, such kind of honor relationship is very important. So how? That's in the physical life. So how about in the digital life? How the blockchain can describe and protect such kind of honor relationship? You create a network, you try a network, you have some data to write into the blockchain, you have some coin in the network. How you prove to the other people that that's your coin, that's your data, but not the other? How can only you have the permission to access, to use such kind of data, but not the other? So in the blockchain, to protect such kind of honor relationship, is use the asymmetric cryptography, such as the RSA encryption. And then, because in the blockchain as well, because there's a lot of people, a lot of data will be written into blockchain ledger. So the ledger become very big, maybe several gigabytes of data, several terabytes of data, a lot of data. But on the user, on the miner of the network, they need a mechanism to verify whether there is any modification, any delete of data in the ledger or not, unexpectedly modification or not, quickly. So to verify such kind of quickly, so the blockchain use a technology is called cryptography hash function, such as the SHA-256, SHA-512, SHA-3, and so on. Yeah, and another very important technology is the blockchain consensus. Why isn't it? Because the blockchain is a decentralized network. Not only one person write the data into the ledger, but a lot of miner write the data in the ledger, and the miner may be honest, work honestly or dishonestly. We don't know. Therefore, we need a mechanism to force on the miner work honestly, and that's such kind of mechanism we call is blockchain consensus, such as the proof of work, proof of stake, delegate, proof of stake, and so on. Okay, so just shortly explain about asymmetric cryptography. So when you create an account, it means that you are running asymmetric cryptography algorithm. You create two address. We call it public key and private key. So the public and private key, so if you encrypt data by using this key, you can decrypt such data by using the public key and vice versa. And in the blockchain, we use these two keys in two cases. The first case is public to private. When you want to send the data to someone, you use a kind of public and private key. And you use the private to public key to operate as a digital signature. I will show it more clearly in this slide. So let's say in the network, we have the user A want to send the data to the user B. So firstly, he used the public key of the user B here to encrypt the data. And then he used his own private key to sign into this message. And this message will be sent to the mining pool. The miner will get this transaction data and then use the public key of the A here to check the signature of the A. And then if it's passed, so he will write this data into blockchain ledger. And as the receiver, he go to the blockchain network to get the data and use his own private key to decrypt the data to see it data. Yeah. And this guy we call is public to private. And this is the private to public case. Okay, the next is the crypto hash. Okay, let's see this blockchain ledger. We have a lot of blocks connected together. And in each block, we have a lot of data, transaction data, and we need cryptography hash function to generate the Merkle root of this transaction. And then from this, we form the header and use the cryptography hash to calculate the hash of the header. And in block, we have transaction data, the hash of previous block, and the hash of current block. Yeah. And by this mechanism, so all the blocks connected together via the hash value. And for the miner, he only needs to check the final hash of the final blocks. So he can know that whether is there any data inside any block already been modification or not yet, very quickly. Okay, the consensus. Okay, let's say in the network, we have a lot of user creates a lot of data. He wants to write the data into a ledger. And also we have a lot of miner. He want to write such data into the ledger. But finally, the network only have one ledger. So the result of which miner will be accepted. So in this case, we need to use the blockchain consensus. So let me explain about the proof of work consensus. So the basic idea of proof of work consensus is that the system security is trade-off by using the energy consumption and computer resource to trade off the system security. By it means that it give a penalty for the dishonest behavior is very expensive. Therefore, it can avoid the try to attempt action. Therefore, the network can be safe. So that's the idea of the proof of work. Okay, so let's see how the proof of work create a new blocks. Let me give an example of the Bitcoin network. So in the Bitcoin network, a lot of transaction data is put in the mining pools. So to generate a new block, a miner needs to go 3 steps. In the first step is calculate the Merkle tree hash of the transaction. that he wants to write into the block. And then step 2, form the header. And from this header, it generate the hash of the header by running the double SHA-256 algorithm. And to run the proof of work, and the miner needs to run the double SHA a lot of time by changing the nonce value in here until it finds the hash value that meet the target value here. So it says that the total Bitcoin network needs about 10 power 37 times repetition of calculate the double SHA-256 here to create a block of the ledger. So that is the key reason, the main reason why the Bitcoin network consumes a lot of power consumption nowadays. So therefore, the research, there's a lot of research on accelerating the double SHA-256 algorithm in here. And also because of that, so the current proof of work, they have two main basic disadvantage. The first is that very huge energy consumption. As you see that this is a report of the energy consumption of the Bitcoin network. So it consumes even more electricity than several countries like US or Switzerland and so on. And the next disadvantage is the centralized likewise. You know that one of the advantage of the blockchain network is the decentralized. But now, because of the proof of work like that, so it's centralized likewise. A lot of computers cooperate together in a mining pool so that to be able to create a new block to get the benefits from that. Therefore, it's become centralized likewise. Okay, so in our works, we want to solve such problem by focus on accelerating the double SHA-256 algorithm. So let me explain about first the research target. In our target, we want to build a tiny blockchain accelerator BCA that can win the giant GPU Tesla V100 on doing the Bitcoin mining task. And of course, not only Bitcoin mining, but also the other blockchain network. So for the future vision, with the BCA, we hope that the smart device like self-driving car, smart clothes, smart watch, smartphones, and smart shoes, and a lot of smart but power constrained device can using my BCA to become a BC blockchain gateway to enjoy and participate in secure the blockchain network. And also it can help to fostering the IoT and AI industry. Okay, so let's see about how the future use. I'm looking at the self-driving car ecosystem. When you want to build the ecosystem, I think you need an accelerating put inside the car, to do some processing necessary for the proof of work or blockchain pre-processing. And in such case, you can use our BCA for low power consumption. Yeah. Okay, so let's go in more detail about the processing inside the double SHA-256. What is calculate? Let's see now we have the header here. The header here I get from the Bitcoin network header, but actually the other blockchain network, the header is somehow similar to this. And to run the double SHA-256, it needs 3 blocks of SHA-256. So the first SHA is get the first 500 bit of data, and the next SHA get the next data, and the final SHA is for double SHA, double again the hash calculation. And in this header, notice that only the nonce here, the nonce data is changed for one block to create the header for one block. So the other data does not change, but we only change the nonce data here. up to 2 power 32 times to try a lot of trial to try to find a final hash that meet the target. So it means that to calculate the double SHA here, the SHA-256 block 1, we need to calculate it only one time. But for one-time calculation of SHA-256, the SHA block 2, we need to calculate it up to 2 power 32 times, equivalent to the 2 to power 32 times of the nonce value here. And when the SHA-2 dissolve of SHA-2 is changed, the SHA-3 need to recompute it again. Therefore, SHA-2 and SHA-3 need to compute up to 2 power 32 times for one time of SHA-256. So in our circuit, we try to accelerating the SHA block 2 and block 3 only. Yeah. So let's see inside the operating of the SHA-256. I do not go in detail, but basically the SHA-256, it follows two processes. The message expander ME process and message compressor MC process. So basically this process, they repeat a lot of loops. So the important note is that to calculate one value of the hash, the SHA need about more than 2,000 simple operators like logic gates, shift adders, and so on. And they need to follow multiple loops. And more important, very important, the calculation inside the loops has the data dependent among the loops. Because of these characteristics, the current hardware platform like the general platform like the CPU or GPU, they do not have the well performance on computing the SHA function yet. For example, let's look at the GPU Tesla V100. Is one of the most fastest high performance GPU nowadays. So, but basically it's aimed for the AI learning. Therefore, most of its hardware resource is focused on calculate this such kind of convolutional. It's not suitable for it's very high complexity, but it's not suitable for the cryptography hash function. Even though it still can calculate the hash, but it's not optimal for SHA function. And the second point is that the memory data, the DDRAM L2, L1 cache, placed far from the calculation unit is not good for the SHA calculation because SHA, there's a lot of data dependence among the loops. Therefore, we propose a new architecture. That is we have the calculation unit ALU located near the local memory inside each processing element to solve the data dependence problems. Yeah. So another question is that currently we also have a lot of similar architecture, CGRA based architecture. So why the existing architecture does not have high performance on the SHA calculation yet? The answer is that each PE here is basically quite small, and therefore to calculate the SHA, we need a lot of PE. We need to configure a lot of PEs, and during the configuration, some PE maybe is not suitable and cannot be used inactive. So it's quite losing the hardware efficiency is not good. And the mesh network causes the high complexity. And the next problem is the data dependence. When we connect several PEs, and because of the data dependence that need the calculation inside this PE require the data from the previous PE, which is impossible. Therefore, we need the data transfer request many times. That it was the resource and low speed. That's the disadvantage of the current CGRA-based architecture. So how about our architecture? How we can solve such kind of problems? We have several ideas to solve the problems. The first idea, we propose the pi-like ALU that can calculate on the loop of the hash function inside a single piece. And then the second idea, we use the multi-local memory structure to efficiently use the ALU architecture. And the idea three is the double cell PE to compute both SHA block 2 and SHA block 3 of the accelerator of the double SHA inside a single processing element. And idea 4, nonce auto update. Yeah, for more detail, I will explain later on. But firstly, let's look at the overview of our architecture when it's used in the embedded system. Like, yeah, we have an embedded system here. You can use our BCA by connect it with an ASI bus interface. And the embedded system can connect with the blockchain network via the network interface connector like this. Okay. And this is the overview architecture of the BCA. So the main component of the BCA is an array of double cell processing element, DPE here. And inside each DPE, they have two cells. The cell 1 and to calculate SHA block 1. And cell 2 is to, cell 1 is calculate the SHA block 2 of the double SHA. And cell 2 is calculate the SHA block 3 of the double SHA. And inside each cell, I use the pi-like ALU architecture and an array of multiple local memory divided into the WRAM and HRAM in here for efficiently using the hardware architecture. Okay, so in case you want to, in case you want to scale the processing rate with the power consumption, you can use several blockchain accelerators, concatenate it into the same ASI bus to increase the processing elements. So let's say we have one BCA have 64 DPE. So you think that is not enough for your requirement yet, so you can concatenate several BCA to speed up processing rate multiple times like this. Okay, so let's go into the ideal one, the pi-like ALU. In this architecture, so we have the hardware circuit to calculate a loop of the SHA-256 in 4 pi-like clock cycle. And then the data is feedback. So that all the loops of the algorithm can be computed inside a single ALU. And final loop, we have several actors to calculate the final hash value. Okay, and in here, so this is the detailed architecture of the DPE. It have include two cells in here. We have the pi-like ALUs, an array of 4 blocks of the WRAM and an array of 4 block of the HRAM. Yes, I think for more detail here, so if you want to understand more detail about this architecture, so please contact me. So I will send you the paper that I already published. That in this paper, we explain more detail about this architecture. Yeah, and inside the cell 1 here, we have a circuit we call that nonce auto update. That it can automatically update the nonce value, so that each DPE they can repeatedly calculate a loss of hash function by changing the nonce value. And then in the cell 2, after they get the result, there is a circuit to check the hash value, to check whether the hash value meet the final target or not yet. So if the final values meet the target, so the chip stop signal will activate to tell on the PEs of the accelerator yet, oh, I already find the valid hash value. You can stop working like that. So on the PEs can stop working and the valid value will be read out of the BCA. Okay, so for the nonce value, yeah, as in the header, you can see that for the same value, so we can change the nonce. For the same header, we can change the nonce value and make a lot of trial to find the valid hash. So inside a single DPE, we have the WRAM here, block here. They store the initial input data. And the initial input data like W0 to W63. All data are the same except the W3, which equivalent to the nonce value. So in our architecture, for calculating the first hash function, so it read the nonce value here, calculating, and after they get the result pass to the shell 2. So it will automatically update the nonce value, increase the nonce by one value, and then try the hash calculation again with the next value of the nonce. So by this mechanism, a DPE can repeatedly calculate, check on the nonce value until it can find the valid hash. Okay, so let's look at the outside view, the view of the BCA, the view from the CPU, how the CPU view our BCA. So it looks like that. This is the memory map that the CPU views my BCA architecture. So the W01 until H1 here, so it's equivalent to the input data necessary for calculating the SHA block 2. And W02 to H72 is equivalent to the input data necessary for calculate the SHA block 3 in the double SHA. And W0 to H0 to H7 here. This is the valid hash value calculated by our accelerator, the result output, the output result. And the CPU will read this hash value and use this hash value to broadcast to the entire blockchain network. And the non-star and non-step here, what is this? So the non-star is the value that the outside CPU, they tell to my BCA that, oh, I need you to work, calculate the hash value by start with this nonce value. For example, usually the nonce is start from 0. And the nonce step is tell the BCA that in each DPA, you will calculate how many value of the nonce. For example, let's say in the BCA, we have 64 DP processing element. So each DPE is calculated for 1,000 value of nonce. So in that case, the nonce step will be 1,000. And the DPE0 calculates the nonce value from 0 to 1,000. The next DPE calculate for nonce from 1,000 to 1,099. And the next DPE is from 2,000 to 2,999, something like that. And on the DPEs, they work independently in parallel to compute the accelerating the hash. A lot of time, yeah. Okay, so what is our experiment result? So we have run the simulation to calculate the double SHA in several hardware platform like the Intel Core i9 or GPU RTX 3090. This is very fast GPU nowadays. Is fabricated in ASIC 8 nanometer technology, very fast technology. And the GPU Tesla V100 is also very fast GPU Tesla nowadays. So the price for the RTX 3090 is now about $2,000 for one board, and the GPU Tesla is about $10,000 for one GPU. Yeah, it's very expensive because it's high-end technology. And this is our proposed BCA. We synthesize in the FPGA. The other board is ASIC, the other hardware platform in ASIC, but our is in FPGA on Arvel U280, and we run at 400 megahertz. And the power, we evaluate in terms of the power, processing speed, and power efficiency. And as you can see here, this is the power and the processing speed of several platforms. And you can see that the BCA in FPGA is consumed such kind of power, and the processing speed it can achieve almost the same processing speed with this GPU Tesla and GPU RTX 3090. So in terms of power efficiency, the BCAs can improve the power efficiency as compared with the CPU Core i9 by about 600 times, and compared with the RTX is 32 times, and compared with the Tesla V100 is about 21 times. But you know that this is we synthesize is different technology, ASIC and FPGA, and also the nanometer technology also different. I think in the future, if we make the ASIC chip of this BCA, so it can even more achieve even much more hardware power efficient performance. Okay. So for our prototype blockchain system, so we also developed we do not only develop the accelerator to accelerating the SHA function, but also we develop the prototype system. We focus on the blockchain consensus because we think that blockchain consensus is one of the most important factors to contribute on the successful of the blockchain network. And to go deeply inside the blockchain consensus, so we need to develop the prototype system developed by ourselves. We do not use the like Ethereum smart contract platform or Hyperledger platform, but we build it by ourselves so that we can easily edit the code according to our algorithm. So in this prototype, we developed the system by using the Golang and Python, and also we interact our miner, interacting our prototype platform with the mining hardware with the UART. So we develop it by ourselves. So previously, we also used the Ethereum smart contract platform to build some prototype system like the medicine management system or healthcare monitoring system. But we see some disadvantage when using the Ethereum platform. So therefore, we develop the platform by ourselves. And currently, this job is ongoing job. So we do not have much to tell you. But yeah, I just want to tell you the brief overviews like that. Yes, that is all for my talk today. So welcome to your question, comments, or any advice to my talk. Thank you so much.
Thank you, Professor Tran. I have actually a comment from Andreas when you were speaking about the Bitcoin network. I will read it to you. The network is only safe as the economic value at risk of all the miners together mining blocks. If the miner extractable value from on-chain assets through collusion is significantly larger than
Yeah.
the value it can get from mining, then we have a security problem. He also goes on to say that he provided a link for a study about the topic. So I just wanted to add that. And Andreas, please chime in if you'd like to elaborate.
Yes, thank you so much. So you mean that so I can contact you later for
Sure, I
yeah,
can put you in touch.
yeah.
Are there
Thank,
any other
thank you so
questions or
much.
comments? I think people are being a little shy. Oh,
Yes, I'm
here's
sorry
somebody.
because okay.
uh, this is from BC. His initials BC. How much hash rate is too much?
How much hash rate is too much? I'm sorry. Somehow understand your question, but somehow I do not understand it. So, what do you mean for how much hash rate is too much? I think there's no too much for the term hash rate because actually we want to achieve the hash rate as much as possible, as fast as possible. But we need to also consider the power consumption and the compatibility, whether it's easy to use or not. For example, here, yeah, of course, if you want a lot of, you want to faster processing speed. For example, if you use the GPU here, you need faster. You can buy a lot of GPU, concatenate a lot of GPU, but then you need to pay the cost of the power consumption and the cost to buy such kind to buy the GPU. Therefore, everything have the trade-off. And yeah, so I think don't have the limitation on how many mega hash per second instead of processing speed. That's my opinion. Yeah.
BC, you can unmute yourself. Anybody can unmute themselves if they'd like to ask another question. Okay, I think we're going to wrap it up. Thank you again, Professor Tran, for giving our participants a window into your work and into the work of your lab. It is fascinating and gives us much hope for the future.
Yes, thank you so much.
Thank you.
Yes,
have a wonderful day, everybody.
Yes. Have a wonderful day, everyone. Bye-bye.